All right, guys, welcome back. Let's finish up this lesson on work. So here's an example you guys have in your workbook. We're going to start off, and I do recommend you guys try this question yourself first. You can pause, give it a try, then we do this one together. Let's draw the box. 17 kilograms. It's going to experience a force to the right. We're going to call that applied force F, and it's moving to the right. So there's its initial velocity, but there's a 120 Newton friction force. There's our FF of 120 Newtons, and it's going to cause it to accelerate backwards at 1.85 meters per second squared. And there's our goal. Our goal is to find the work done by F. So let's put that kind of in front of us. We're looking for the work done by F, which will be F delta D cos theta. And that's what we're going to use as a reference all the way through this question, because this actually isn't like a recipe. If you want to find the work, you've got to find F delta D and deal with cos theta. So let's do them in order. The very first thing we're going to do, let's find F. And this is going to be a nice review. We just have to use Newton's laws and do force diagram analysis. So I'm just going to copy that and bring it down. Move it over here, shrink it a little bit. Okay, I'll just leave it the way it is. Okay, and let's put a reference system on this. We're going to say to the left is positive and to the right is negative, since we want to go in the same direction as the acceleration. All right, so that's going to be Newton's second law. F net equal to ma. FF will be positive because it's to the left. F will be negative, equal to ma. And we expect F to be less than 120 because it accelerates in the direction of FF. So we discover that F becomes equal to FF minus ma, or 120 minus 17 times 1.85. And that gives us about 88.55 newtons, less than 120. Things are going well so far. Okay, next, and I'll transfer this down. Our next step is to find the delta D. To do that, I'm going to go back and just going to copy this question actually. I almost had that. Copy that. I'll just put that over to the side. It's going to be nice and small. All right, so our next objective is to find delta D. This is going to require us to do some kinematics. So we do V initial, V final, A, delta D, and T. And interesting enough, I'm going to tell you that if you want to, you don't have to use the same reference system that you did for the force diagram. You could, if you want to, choose right as positive this time and left as negative. Or you can stay with the same one. It's really up to you. But it's a different analysis. You can use a different reference system. So in this case, V initial is going to be 9 meters per second for me. If you go with the original reference system, it's -9. V final is 0 because it comes to rest. The acceleration in my case will be -1.85 meters per second squared because it's going to the left. But again, if you choose the other reference system, it'll be positive. We're looking for the displacement. Time doesn't play a role. So now we do V final squared is V initial squared plus 2A delta D. If we get delta D by itself, you should get V final squared minus V initial squared over 2A, as many steps you need to show. That's going to give us 0 minus 9 squared over 2 times negative 1.85. And that comes out to be about 21.89 meters. Okay, and then we're ready to finish. So remember, this, well, I don't think I need to draw that again, but I'll take the diagram again, the force diagram. That whole thing, let's copy that. Paste it, shrink it, bring it over here. So now we can go back to the original equation, and we have work is equal to F delta D cos theta. So that means the work done by F becomes equal to F delta D, and the cos theta just really is a positive or negative work. Because the force goes the same way as the velocity, same way as the motion, that'd be positive work. So it's simply going to be positive, the F, which was 88.55, times the delta D, which is 21.89, and this one comes to be positive 1.94 times 10 to the third joules. So this is a more involved question for sure, but when you're doing these kind of work questions, definitely write down the equation first to kind of guide you for what you have to find. And it's like a recipe, like I said. First thing we're going to do, we're going to find F, and we do Newton's laws and force diagram analysis. Then we need to find delta D, and that requires kinematics. And for cos theta, it's just, is it positive or negative work? Does it go with the motion or against the motion? And that's it. All right, so hopefully, and again, that's a really important question. Lots of marks kind of attached to it. So definitely get some practice on that. Now, just one more thing. We've been dealing with the work done by a constant force. Now let's do a work done by a changing force. So to do that, I'm just going to show you, let's show you a graph, because that's how we typically show changing forces. But in this case, the force is constant for the one I'm showing you here, constant 10 newtons. And that means we can actually use the formula work is equal to F delta D, because the force is constant. But that in that case, it's going to be 10 newtons for the force, and the displacement here is 5 meters. But as I've shown you before in the first unit, the 5 meters happens to be kind of the length of that rectangle, whereas the 10 newtons is the width of the rectangle. And therefore, can you see this actually comes out to be essentially length times width, or area. So all we have to do is to find the area under the graph. It is the area between, specifically the line and the d-axis. If it's above, it'll be positive work. And if it's below, between the line and the d-axis, it would be negative work. And that's all you guys need to know. All right, you know everything you need for the homework. I wish you guys all the best, and I'll see you in the next lesson.